So the default value should be whatever the DP value can take, right? 0, plus infinity, minus infinity. Okay. So this is the recurrence. So what would be the complexity if we try to calculate using this kind of recurrence? So first of all, let's understand the complexity. Now, this will be, now in general, when you want to calculate the time complexity, like if you want to calculate the order notation for this, the thing that you can use is find out the number of states that the DP has. Okay, find the number of states, multiply it with, very important, average number of transitions. Okay, average number of transition across all states. Average number of transition across all states. So by transition, I mean to say that, okay, from this state, we can go to these all states, right? These all states value are needed. Like there are some number of states on which we are going to, right? From taken to I. So these are the number of transitions that can happen from this state. Okay, that's what we are talking about. So this is the number of transition. And we want to find average number of transition across all states. And that is what we are going to multiply with state to get the time complexity of any DP problem. Okay. Please note this, that this is average and not like maximum. There is a purpose for this. We will take up some problem in which this will come up into play. Okay, so in this particular problem, if you think about how do we look at time complexity for this, there are two states, right? Now, since the actual value was n, the input is only n, we need to write answers in terms of n. So the first, like the numbers that we have to decompose can only be from 0 to n. Like we have to decompose either 0 to some number n, and the last taken value can also be from 0 to n, right? So the total states can be n cross n, that is n square. And from every one of them, you can on average take linear number of transitions, right? It can be taken to I. So on average, that will be around order n itself. Okay. So number of states is n square and the number of transition is order n. So the total complexity of this would be order n cube, right? Make sense? Is this clear to everyone that like using this, suppose this is true, of course you might have understood that why this is true, because every DP state is calculated only once. Okay, yeah, it has overlapping subproblems, right? We might reach the same taken value repeated times, like from two different values we might reach the same value. Like it is perfectly possible that this might have repeated values. So yeah, so you can think about repetition in this sense, right? Like let's say there is a sequence 1 1 2 and there is a sequence 2 2. So they both lead to same thing and the last taken is 2, right? So this state would be repeated in both this sequence, right? Like there is some n and your starting few moves are something like this. So they both will reach into this state. Is it making sense? Like this particular state will repeat, right? Whichever state is this. So there are repetition of states. Okay. But is this the most optimal that we can do? Let's look at that first. Okay. So let me quickly move a bit up here itself. And this is the transition that we have right now, right? So let me write one more like similar type of transition that we can think about, DP of I comma taken. Okay. I will write it as DP of I. Like I want to make I and I take taken, whatever the taken value was, I take that much number again and I still have taken. Okay. Plus DP of I remain with I and I make taken equal to plus 1. Okay. And what I claim is even this is correct. Why? Like think about how this is working. From this particular state, okay, I either have a choice, like the last taken number was taken, okay, and for the next number what I have is I can either take same as taken, okay, or if I don't take same as taken, at least my taken will increase by 1, right? So what I can do is I can keep my I as the same value and I can move the taken to plus 1. Okay, so now I basically am enumerating on those choices where I have some sort of new moves available at higher places, and those all will be counted by this particular part of the recursion. And if I take the same value again, then that is counted by this particular part. Okay, So in fact, this is counting the same number of moves that is possible. It's just that instead of this summation, we now have just two terms. Okay. So this part will optimize on the number of transitions to be order 1 because there are just two states on which it's depending on. Okay. Okay. Why is this working? Why this state is working? That's important. So let's say you have dp of I comma taken. Okay. Now let's say you are taking something like this, like you have taken 1 1 2 and your taken is equal to 2. Okay, last value is taken is 2. So you are at, let's say you had to make 7. Okay, and you took 1 1 2. So you are currently at the state, like you are left with 4 and you have taken the last element as 2, and now you have to decide on how to generate the rest of the elements, right? This is the number of ways in which you can generate the rest of the elements will get added to the previous values of recursion. Okay, now when you have 4 2, what we can do, either we can take 2 again, right? This is one possible choice. So that will be taken care by this particular part of the recursion, right? If we take the same value again, or else it will be either 3 or 4 or 5 and so on, right? This will be either 3 or 4, something like that. So what we can do is we just make a transition to dp of I comma taken plus 1, like 4 comma 3, that now I can use only things greater than or equal to 3. So either I was taking 2 or I can use some element greater than or equal to 3. And by the property of my dp, what is my dp? Like, don't think that my recursion, like if I do a transitions, I might be wrong. If I design my transitions correctly, if it's enumerating all the possible choices correctly, my dp will return the correct value irrespective of how I configure them. Okay, so my dp is given a I comma taken, it will generate in a sorted sequence, and it will count me the number of sequence which will give me the number of sequence which will give me a sum I. Okay, with the first value greater than or equal to taken. Okay, so my first value is greater than or equal to taken, so either this particular value will be taken or it will be greater than or equal to taken plus 1, right? So that's what the two choice that in which we are breaking it into, and both of them will count independently. So the total number of choices will get count and nothing will overcount, because these are two exclusive choices that we are doing over here. So that will actually count our dp over here. Okay, so basically, let's say let's understand with one small example. Okay, so let's say I just took 1 before, like I need to, let's think about this state. I need to make 5 with last value taken as 1. Okay, I need to make 5 amount is left and I need to make 1. Okay, so either I can take 1 over here, which is counted by this. So let's not consider this. Okay, so you will say, how am I counting, let's say this particular sequence? Okay, 3 will not even work in this case. Let's make it 6. Okay, so let's say where am I counting this particular permutation? So when I'm going into like 6 comma 1, I can go to dp of, like I will count the number of permutation which can be formed in this fashion. Okay, and I will also this will count 4 comma 2, or this will count 6 comma 3, right? It will go to plus 1 or it will subtract then and there. So now when I come to this particular state, this will count this particular sequence by going 3 twice. Like it will take 3 once, take 3 once, and go on, right? So this is how it will enumerate on all possible sequences that can be generated. Like either it's greater than taken, either it's exactly equal to taken, or it's greater than equal to taken plus 1, right? So these are the two choices in which I'm jumping into. Okay, and then as per setup of my recursion, I know my recursion is counting correctly, so this will count correctly. And since using this value and this value, I'm constructing this value correctly, so my overall recursion is correct. So when you want to convince yourself that my recursion is working correctly, this is a very important thing, that how do you convince yourself my recursion is correct? First of all, assume that your recurrence is correct, and your this like exactly. Let me explain that. So let's say we want to find out why my recursion is working correctly, or if I've taken some state, is it correct or not? Okay, so first of all, assume that your states are correct and your dp will return whatever you are thinking will correct, like is correct. Okay, let's assume that. Then think that, okay, whatever you are summing up for dp of some I comma x, okay, using its smaller states, is that combining correctly, giving me the value for I comma x using the smaller values? Assuming that it's like giving correct for the smaller ones, is my bigger one computed correctly? If that is working, then it will work for every case. Okay, it's some sort of induction going on there, because if smaller ones are working, you assume smaller is working, and from that bigger one is correct, so everything beyond that is also correct, something like that. Okay, now how is this counting everything? Think about this, right? Like at once, like let's take this sequence that you have, just like over here, that we had 6 and last element was taken as was 1, and something was going on before, and last element taken was 1. Okay, so over here we can place 1, 2, 3, 4, 5, 6, right? These were the 5 choices that we could have placed over here. Okay, now what we do is we either place 1 over here, or we like take all of these together and we say that okay, we can place anything from 6 to, like 6 to will count what are the different number of ways of this particular part using the options 2, 3, 4, 5, 6, right? This is what this particular function will count. This function will count what is the number of ways in which we can break down 6 using 2, 3, 4, 5, 6 placed in the first position, right, out of these things. So that's what we are doing. We are just going to this state, or we are using 1 itself, okay, instead of looping over each and every one of them. Okay, this is making sense now, that this is the number of choices that we have at this position, right? At this position we can place 1, 2, 3, 4, 5, 6, but once we place a 5, we know that we can only go to 5 or more. Like after that the DP state would be 6 minus 5 comma 5, something like that. Anyways, this is no longer possible, but still. Okay, so this particular transitions we divide into 2 parts. One is just using 1 then and there, and the rest of the things we just move the taken plus 1 to higher value, and then that will restrict it to this much domain. Okay, and then from this one we will again transition to either 4 comma 2 by using this move, or we will go to this much of choice by 6 comma 3. Okay, this will allow you with only these positions at this particular place, right? So that's how it's enumerating on all possible choices. If you can just print the brute force and like look into the recursion, that's also one way you can look into why it's generating it. Okay, like at every choice, if it's enumerating on all possible values, then it will of course give me the correct choice, right? And by sorted sequence we have already eliminated the choice, like possibility of having any duplicate sequences. Is it clear? Okay, so this is how. So from one state we had, like let's say 5 number of transitions. So what we did is, okay, we know that some of all these transitions can be like taken from one different state. That's what we did, right? A lot of so we were doing a lot of transitions over here, but we know we looked at it and we said that okay, that's a lot of unoptimized operation there. We could have taken all those transitions to some from other state value, because it's already being calculated over here, so why not take it from there itself? Okay, and which in fact reduces the complexity a lot, because now the number of state is order n square itself, but the number of transitions becomes order 1. So in total the recursion becomes, the total DP complexity would be order n square itself, order n square only. Okay, so that's why along with states and these what do you store in DP, transitions are also important thing that you should think about, because the way you design the transitions will also dictate what is the complexity of your code, right? The more efficient you design the transitions, the better it is. Okay, instead of looping a lot, can I go to some state which already computes the same thing, okay, sum of all those values? If that's possible, then that's well and good, right? Because it's already like a lot of computation reduced. Make sense? So this is one problem. We will, okay, so this is like a n square method to calculate partition numbers. Of course there are like even faster method than this, but that are highly advanced maths. Okay, so let's move into the next problem. Like today we will be mostly focusing on what are different kind of states and the things. We will discuss 1 or 2 codes, but most of the things will be on like, yeah, sure, go ahead, Abhijit. Yep, that's correct. Is that all, or you are asking something? Okay, so dp of I has taken is taking the same element. Yeah, you are taking the same element again. Okay, yeah, that's correct. So in short, dp of I comma taken means you have to create a chunk of I, and the first element now can only be greater than equal to taken. Okay, this is what you're doing. So from this, we are breaking it into two parts, summing it through two things, that you either put taken over here, and this part is remaining, and this is I minus taken, and you have to place greater than equal to taken over here, or into this part that uh, this is again I, and you have to place greater than equal to taken plus 1. Now see that these are both mutually exclusive. Okay, how does this help for taken plus 2? Because due to the same transition from dp of I, like just how we went from I from taken to taken plus 1, taken plus 1 will go from taken plus 1 to taken plus 2 as well, right? It will count that particular method as well, that particular part as well, because from here we consider this particular breakdown, right? This particular breakdown. Now this will break down into two other parts. One is, let me explain how this is working. You are placing taken plus 1 over here, and then you are left with I minus taken minus 1. Okay, and this greater than equal to taken choice over here, or you go to I, and this will be greater than equal to taken plus 2. Okay, so this is how my recursion is calculated. Like actually we had to calculate sum of these value, like this value plus this value plus so on, whatever these values were going to calculate, right? Whatever these values was going to be there, like greater than equal to like, sorry, this is taken plus 1. So either you take taken and it's still greater than equal to taken, or you take taken plus 1 and still greater than equal to taken plus 1 plus taken plus 2 and so on. But what we did, like as a optimization, is we just took this particular part and that is summing up everything over here itself. Okay, so we don't have to write all those things. So this is how this like recursion is working and it's calculating the things. Okay, so basically you have to have faith on your recursion that okay, it will calculate correctly. Okay, unless you are not counting any particular permutation twice and your smaller states are working correctly, your bigger ones will work correctly, right? That's all. Okay, so you have to just prove at one step that it's counting correctly. Okay, okay, let's move to the next problem. Now let's start with some classical problems. Okay, so that was not a very classical problem that we discussed, but it helps you to think about what's the importance of having states, having correct states and having correct transitions. Both are very important, right? Because they can decide on your complexity by a lot amount. Okay, and like n cube and n square can be a difference between TLE and AC, right? Okay, so now we are given a some simple array and you need to find the sum of like a sub array which has the maximum sum. Okay, now let's say 3 minus 5, 4, 3 minus 2, 1. Okay, something like this. So in this case, the maximum sum subarray would be something like this. Okay, had I made this particular part equal to, let's say 5, then the maximum sum subarray would have been this part. Okay, like this sum would have been equal to 5, 5, 10. This sum is now 7. So based on a given input array, find out what is the subarray which has the maximum sum subarray. Okay, now this is a very classical problem. I would not be leaving this for long. This is very classical, and there is one standard algorithm which is called cadence algorithm. Okay, you can look this up on any platform. This is very like interview or intern specific top problem, and this is like I think very simple, and you can have a look at any platform, you will get the answer. But what we will do today is we will build the DP idea for this. There are two solutions, one is cadence based and one is DP based. Okay, so we will build the DP one for today. Okay, so how do we find the maximum sum subarray? So for this we will also again define a state. Okay, so we will define a state called DP of I. Okay, now DP of I will give me maximum sum subarray ending at index I. This is what we want to calculate. That what is the maximum sum subarray that ends at index I? Okay. Let's say this is what we are trying to calculate. Make sense? So at every index, there will be at least one subarray which is of maximum size, right? Like every index will have some potential value. Like this will have 1, this will have 4, this will have -1, this will have 4, just this will have just 4, okay? Because it's no longer optimal to go beyond this and take all of these things, right? So we can take this kind of DP state to be like finding the maximum sum subarray that ends at index I, okay? Now you might be thinking of a lot of different states, but let's think about this particular state. How is this even working? So if we want to calculate the answer for some ending position I, okay, how do we actually do that in this particular position? So there is one particular observation that you can take is, like, let's say this is the subarray and this is the position I that you want to calculate answer of, okay? There are only few choices. There are, if you talk about all choices, it's like either it will be just this or this much, like, or this much will 3 elements, or this much or 4 elements, and so on, right? This is clear, right? These are the only possible choices, right? All possible subarrays that start from this. Now out of these, if I just quickly subtract, like these are different sums, right? So if out of all of these I just subtract the value of this particular array, okay, so this is nothing but, like, there is 1 which is 0, plus from over here it's starting and going to 1 element, from over here it's going to 2 element, from over here it's going to 3 element, right? Plus this element, this 1 element is over here, which we are subtracting out because it's common in all subarrays, okay? So that is going to get added to this particular index irrespective of whether whichever subarray we take, right? Now out of these things we need to decide on which subarray we take, right? Now think about these particular solutions, like these particular spaces, okay? This is nothing but the space that we had for this index, right? For this index, these were the 3 values out of which it took the max of, right? So we can simply take the max of answer of this particular index. This is 0 because this is no element, plus this particular value. So let me explain it once more, and that I think will clear this up. So what we're trying to do is we were trying to write it something like this. dp of I will be equal to whatever the value at I is, because that we have to take irrespective of what we have, okay, plus max of, either we take this one or we take this one or this one or this one, we club this all together. So max of all of these, and max of all of these is nothing but the value of this index dp. Why? Because that's what the scope of this was, right? If you think about scope for this one, it's nothing but this, these are all the subarrays, and out of which this took the maximum value, right? And this value you can calculate using the value of next previous value. Is this making sense? What we're trying to do over here, right? Just understand this diagram well, because like what we are like removing, we are removing one element out of everything, and then this, except this one element, everything else is a part of this particular chunk, which is same as the like space out of which this took the max out of, right? So instead of recalculating this, we just use the answer from this, right? So dp is actually using a lot of recursive solutions. Like once we have calculated, we reuse them, right? That's the whole idea. So that's what we are doing over here itself. And this is just a simple relation that you can use to calculate the dp value. So right, so you can just write this recurrence and just call the dp of some n, dp of last value, and it will calculate the answer, okay? Or you can even solve this in an array format. That's perfectly fine. The implementation wise, it's very simple to write this recursion, right? So you just need to calculate dp of I. Okay, so this is very simple to write in code. Okay. Is this clear to everyone? Can I have +1 if this is clear? I think this should be fairly simple compared to the problem that we already discussed. Okay. Okay. Right. Now let's talk about one more bit standard one. Okay. So let's talk about knapsack a bit, but we'll talk about all of its variants. Okay. So knapsack problem is also very famous. Okay. And it's basically you have a bag which has like W, it can carry at most W weight. Okay. Yeah. Yeah. So the final answer, yeah, that's a good point. Yeah. The final answer would be equal to max of all index I from n to 1. This is important. dp of I, right? So if you just call dp of n, if you're solving this recursively and you are like you want to like store all the values into some array or somewhere, you can just call dp of n and it will calculate all dp values because everything is dependent on its previous one. But if you want to calculate the answer, that is going to be this particular metric over here, because this maximum sum subarray can end at any position, right? So you need to take the maximum across all positions. Right? Is this clear? Because what we are defining as the state is dp of I, which is subarray ending at I. So out of all I, we have to take the best one. So just take the best one. Okay, that's the whole idea of calculating the answer. Okay. Okay. So this is just the final answer. Now let's talk about the knapsack one. That you have a weight W and you have n objects. Okay, each of the objects has some, let's say, profit if you take it into the bag, and you have to, it takes a weight Wi, okay, in the bag. Okay, every item has a pi and Wi, so it takes weight Wi in the bag, like it takes a space of Wi, and it will, if you take it inside the bag, it will give you a profit of I. Okay, if you sell this bag then finally. Okay, so if you take, let's say, you take W1 and W2, the total profit of the bag will be equal to P1 plus P2. Okay, now let's solve the first version. That let's say every item, there are n items, okay, and each of the item has one occurrence. Like you can either take it or don't, you cannot take it, like there, you cannot take multiple instances of the same item. Okay, so you can just take it once or not, and based on that you have to decide on what is the maximum profit that you can create for the bag. Okay, make sense? And the typical constraints for these kind of problems would be n less than equal to 5,000 and W less than equal to 5,000, right? Okay. Make sense? So this is also a very standard style knapsack, and if you think about it, we have a, like, basically we are trying to build a bag which has a lot of different items to be taken into. Either we have a choice for every item, that whether we take into the bag or we don't take it into the bag, right? So if we directly do it in a brute force sense, we will have 2 to the power n choices, but we want to do it better than that. So we try to design some states, and states that we can keep for this particular problem is dp of I. Okay, and let's say the weight is W. Okay, so let's say we want to, we create a dp of I comma small w. Okay, this is capital W. Okay, this will store that, let's say we have decided on, so I'm just restating it, maximum profit we can create by taking choices in first I items of, and total of, and having a total of weight W. Okay, so what this basically means is there are n items in any order, right? So let's say we call them W1 P1, like W2 P2 and so on, right? W3 P3. Okay, these are the n items that are given to you in some order. Okay, and now you want to decide on whether you can, what is the maximum profit that you can create given the maximum limit of W. Okay, so for the first item you have a choice that I can take it or not, right? So let's say initially you have a bag and you have used 0 items and you have taken 0 weight in total. Okay, so from this you have 2 choices, that either you will take let's say you don't take this particular item, so you have 0 item and 0 profit yet, or you take this particular item, so you get a weight of Wi, okay, W1, and you have a profit of P1. Okay, now Makes sense? That if you take this particular item, you have a profit of P1 and you have to pay a cost of W1, right? So this is I equal to 1. Okay, I equal to 1. And after one item taken into consideration, you have these two choices, right? Now after this, this might be possible that you don't take anything, or you take P, the second one, P2 W2. From this you don't take anyone, that's P1 W1, let's say. Okay, and from this you might take P2 again. From this you at this you took P1, right? So now we can again take P2 from this. So it will be P1 plus P2 plus comma W1 plus W2, right? Make sense? So I have written W over here, but it is nothing but a part of state itself. Okay, so this is the value that we are storing, that this is the profit that we are gaining, and this is the weight of the current bag. Okay, and this is after considering two weights. Okay, so now what we're trying to store in this particular DP is DP of I comma W. Okay, so now W can get repeated, right? Because a lot of different configurations, like let's say W1 plus W2 is equal to W3 plus W4. Okay, let's say this is happening. Makes it like, let's say that this is happening. So in that case, like two choices will come out to be this at the same weight, right? After let's say four moves, there is a one configuration that you take, like you take the first one, you take the second one, you don't take the third one, you don't take the fourth one, and there is a one configuration that says that I don't take first, I don't take second, I take the third, I take the fourth. So these both will result in the same state, 4, that we have taken 4 items, and your current weight is W1 plus W2, which is actually equal to W3 plus W4 as well. Okay, so you both of these reach to the same weight. Okay, so now out of the different configurations that can reach to the same state, we will of course take the one which has the maximum profit, right? Make sense? So out of everything that can reach to that state, we will take the one which has the maximum profit, and that we can only do if that we can just keep track of, because this particular state would get constructed from any one of the state, right? So whichever state from where we were coming, we could design the transitions in this fashion, that dp of I comma W is nothing but equal to dp of, like, let's suppose after I minus 1 we had some, let's say we had a x weight. Okay, and then we added, I'm currently writing this x, but let's say we had an x weight, and then we took ith item. Okay, whatever the weight of ith item was, we took it into consideration, and we got a profit of pi. Okay, and this made it equal to W. So this x was nothing but, let me write it over here, W minus Wi, right? The current W that we are at minus the ith items W. Because if at I minus 1 we had this particular state, that we were at we had processed I minus 1 elements, and we are at weight W minus Wi, and then we took the ith element, then we would have got the profit of P of I. Make sense? And we would have reached this particular state. So this is one possible transition by which you can reach this state. Or the other way in which you can reach this state is you don't take the previous element. So if you don't take the previous element, you were at W weight itself by default, and then you just skipped the previous one, so you reached I. Okay, so these are the two possibilities, and you take the max of these two. Okay, now of course this transition is only possible if this is positive, like this is positive, then only this transition is possible. So if it's negative and other things happening, we know that it goes outside the bounds, and that value gets to default value of dp, that is number of, we need to find the maximum profit, right? So the default value is minus infinity. Okay, is this making sense, what we are trying to design in the dp states? That what is the maximum profit that we can do at after I items and W weight? That either we take I minus 1, either we have taken I minus 1 item, or we have taken I minus 1 items, and we were at weight W minus Wi, and then we took the ith item. Okay, so if we took the ith item, so we got a profit of P of I, and my weight increased by Wi. So if it was at W minus Wi plus Wi, that will become weight, right? So that's how we can transition into I comma W. Or there is the other way, that we did not take Wi, so we were already at weight W, and then we just skipped the ith item, so we came to this particular state. So this is just the recurrence part for this particular problem. Is this clear to everyone? that how we are designing the state, that some states will be repetitive because the different configurations of weight is going to repeat. Okay, that's why we are keeping the weight in the state, so that number of different states can only be like in total order n into w, right? These are the number of states, and every state takes the maximum out of two different states. Okay, so that's going to be order one in transition, so it's going to be finally this complexity, and 5000 plus 5000 is given in the problem, so that will pass. Okay, is this making sense how we are doing this? Is it clear to everyone? Can I have +1 if this is clear, or if you have any question you can ask? So this is just designing the recurrence where most of the recurrence will have this particular state in it, that we have a I which tells which state I am at, and which weight how much I have processed till now, like which all like items I have processed till now, and which weight I have reached. And from this, how could I reach this state? Either by taking the last element or by not taking the last element. These are the two transitions. Okay, that's how you think in these problems. Okay. So this designing is something that you will learn with practice. Like once you solve around 10-20 problems, then only you will see that okay, these type of states are coming very frequently, and that's what you need to know. In fact, we are looking at the most of the frequent states right now, and you will get to understand once I compile this up into different states that we have seen today. Okay. But anyways, is this clear to everyone? Let's move to the second variant of this one. Like it's the same problem as this. It's just instead of having each of the item as having only one occurrence, now we have infinite occurrence of every item. Like we can take every item infinite number of times. Okay. Okay, we can take every item infinite number of times. Okay. So now just a slight change in the transition in the states and transitions will help us to solve the same problem again. Okay, let's say we now have infinite supply, so we write the same states again. In most of the cases, if you see similar problems, the states tends to be the same more or less. If by adding some maybe parameters here and there it might change, but in most of the cases they are mostly same. Okay, so we keep the same state. Okay, that we have processed the first I items and we have reached the weight w, and we want to find out okay what is the maximum profit I can create. Okay, so either I can create it by taking the ith item once. Okay, so it can either be in this form. Let me explain again. This will be the same type as we discussed in the first problem, that either I can take the ith item once. Okay, or I can take the ith item twice. Okay, or I can take the ith item thrice, and so on, unless I till I can take the ith item. Okay, some x times wi plus x times pi. Okay, or I don't take anything from ith item and I go to I minus 1 comma w. Okay, these are the transitions that are possible because now my ith item are available infinite number of times. Earlier we just took it once and then we moved to I minus 1 because we cannot take I again, right? But now I can take I multiple number of times, right? 0 to x. Yeah, so this is this is going to be something like 0 to w by wi number of times if you recurse. Okay, now this is going to be there, this recurrence is going to be there. Out of these we have to take the max, right? Whichever is possible. Okay, similar to this idea that at ith we have w8. So now at I minus 1, what could have been the configuration? That I might have w minus wi, and then I took one of the items of this particular state, and that worked. Then some x times I took wi, so that was w minus x times wi plus x times profit was also added. Okay, or else I did not take any number of times. These are the only choices, right? But again, this has a lot of complexity. Like there is a lot of number of transitions, and in general, it can be order n. Okay, order w. I mean to say. Okay. Okay. Uh, okay. Let me explain that as well. So there are infinite supply. So Let me explain that once. Let me complete this one. So what Vijay is suggesting is, why don't we like, so let's say we are given some item with pi and wi, right? So this particular metric says that, okay, per weight, what is the maximum profit that I'm getting, right? So we, maybe what we can do is we can sort it by pi by w and try to take as many number of times as we can take the particular item, right? So let's try to take some particular case where this might not work. So let's say there is let's say there is two items n equal to 2, okay, and there are the w is equal to 4, okay. There are two items, right? So p1 is equal to 6, w1 is equal to, sorry, let's make this 6 as well. W1 is equal to 4, okay, and then there will be p2 and w2, and we make p2 w2 equal to 3, and this one equal to 3, and this one equal to 5. Okay, so one idea that might be possible is, let's say you have items which has profit and weight, right? So we might take each of the item as many number of times as we can take till it has like a profit of pi, because pi, if pi by wi is more, that means per weight we are getting more profit, right? So it might be optimal to take this kind of decisions, but in most other DP problems generally greedy don't work. And the reason is something like this happens because, let's say these are the two items, so pi by wi is more for the first item, right? So if we take the first item, like in our bag there is a size of 6, so it takes a size of 4. So once we take one chunk of the first item, we get a profit of 5, and my weight reduced, my left weight is reduced to 2. Now I cannot take anything, right? This is one possible thing that happens with greedy. But let's say I'm doing my optimal way, that I can take the second item twice, okay, second item twice, so they are 3, so total is 6, and my total profit would be 3 plus 3 as well. So the total profit will be 6 as well, which is more than 5, okay. So I can do better than just doing greedy, right? So greedy generally don't work in DP cases. Make sense? Now coming back to this recurrence, where we are discussing that how do we write like this, basically how to identify the difference. Either you have to prove the greedy, okay, so either you have to prove that the greedy works, or if both are working, always go for DP, okay. That is the general rule. In short questions, like you don't generally get the time to like prove that, okay, this will work or not. Mostly deep, if you are writing the recurrences correctly, DP always works, right? Greedy might or might not work. So sometimes constraints help you, sometimes you need to go with the intuition that, okay, if you like, if you feel that both are working, always go for DP. But if like you're feeling that my DP is correct, then you might go for it. Like there is no very quick way in which you can like prove it that deep, because DP always works. To check the correctness of greedy, there is like some proof that you will have to do, that either it's working or not. Like either you need to know proof, or you have to do the proof on spot in some sense. So it's generally non-optimal to prove greedy. Either you do it by intuition, or you try some test cases, or these all things happen. In questions you don't get that much amount of time, right, to prove greedy. So that's why if you are good with both, go for DP in a problem. If both of them are passing time limit, go with DP for sure. Okay. So coming back to this particular state that you had, like from I comma weight, I could take any number of times wi and add that many profits, right? Instead of adding these many states, like there would be a lot of number of states over here, right? I can also write it in this fashion. This is non-optimal way to write the transitions, order and number of transitions. I can write it in this fashion. That's it, done. So what I'm doing right now over here is, for DP of I comma W, I'm taking one instance of Wi, okay, one instance of Wi, and I'm keeping the I over at I itself. Note that in the previous recurrence when I wrote, I made W minus Wi plus Pi, and I made I equal to I minus 1, so that I can't take I again, right? But in this particular recurrence, what I will do is I will keep the I at the same place, so that this recurrence again can take wi if it wants to, or it can go to some lower state of I minus 1 comma w. Okay, now this is again the same logic as we discussed in the first problem, because this will enumerate on all possible choices that either you go to the lower state, like either you stop at one taking one element, or you go with one more element and try again with all the choices, right? Is this making sense to everyone? Because this is very similar to what we drew over here. Okay. This is very similar to this one, that we keep at I, we take one instance of wi and we keep ourselves at I, so that we can take I again from this particular state. Okay, either we can take I from this particular state again, okay, or we can go to, from this particular state we can of course go to I minus 1 comma w. So this is of course covered, like this particular state, if you think about when we will calculate it, that will take max out of this particular value. Okay, so this will of course be more than equal to dp of I minus 1 comma w minus wi, right? It will take max out of this, so this is more than equal to this, which is the value over here, right? So this gives us more freedom, that either we can take I again, or we can go to the lower state if we want to. Like we can now we are satisfied with I like number of items of I. Now I want to take I minus 1 its item and previous items, right? This is how we are trying to design the DP. This is one optimization that is very common in DP, that when you have like infinite supply of something, when you have infinite supply, okay, this particular transition works well in problems with infinite supply. In this problem as well, we had like for the taken element we had infinite supply. Okay, so we either kept it ourselves to taken itself, or we moved one step element ahead, right? It's almost the same idea over here itself again, that either we keep ourselves to the same by taking once, or we go to the next possible state. Is this making sense to everyone? Can I have a +1 if this is clear? Just you need to be this much, that okay, if I'm designing my DP correctly, and if I'm passing my values correctly, and if I'm constructing the values correctly at this particular state, then all my DP values will be correct at all positions. Okay, this is something that you will have to build for recursion. Like once you get this intuition very like completely clear, you will be like good with all DP problems. That of course it might be non-trivial right now to when I'm saying that okay, I will take I comma w, how did this I comma w came? So this is something that you will learn from practice. But apart from this, once I take I comma w, why is this DP working? That you will have to understand, because unless you understand this, you won't be able to write this transition. Okay, that which is the main part of DP, of course. And once you write this transition, that how we are calculating this, we can just calculate the values directly on this recurrence. Okay, now this particular problem, let's quickly code this one. I will just quickly code this one, because this is I've not written any code till now, and it might be like vague that how are we going to implement these things. So let me just quickly code this, both the versions, like it will be very similar. I'm taking 1000 values only. So let's say the profit and W's are given to us, and there is a bigger W that is given to us, like this, that much is only possible. Okay, now we want to take let's say integer, let's say we are calculating DP that we have taken up to ith element, and we are left with some W weight. Okay, and then we want to calculate the answer. Okay, so first of all, if I is equal to 0, okay, then let's first take the input. That will make things clear, that how we are storing the things, that this is the n, the number of items, this is the maximum weight, and then for integer I equal to 1, so I'm storing the things in one index. Okay, scene n, scene w of I, scene p of I, so I'm taking 1000 elements only. Okay, right now it can be 5000 as well. So now if I is equal to 0, and w is equal to 0, then we return that there is like 0 profit. Okay, or else if I is equal to 0, or else if I if, so these are base cases of recursion. Right now whatever we are writing is just recursion, right? These are recursive formula that we derived. Okay, now if I is equal to 0 and weight is not 0, so we have done some operation but we have not reached weight 0, so that means it's not possible. So we have to maximize profit, so we will return minus infinity, 1e9. Okay, minus very large value, let's say. Okay. Now once we have defined these base cases, let's say we want to calculate the answer for this particular state. So let's say the answer, we will store it in some variable, answer equal to, let's say, the first of all, at a particular state, if it's not I, what you can of course do is you can move to I minus 1 by not taking anything, right? By not taking the ith element. Make sense? Or what you can do is, and if w of I is less than the weight that you have taken till now, okay, answer equal to max of answer comma dp of I minus 1 comma w minus w of I, right? And this is also something I'm handling in the code itself, so that even if I did not write this, it will work now. But let's take this. Okay. This. So whatever the current w is, current weight is, okay. Can we return 0? So what will be the difference in this case and this case? Because if you're returning 0, then that will not handle the cases, like that is not possible. In fact, you can return 0 in this problem because it will work, because even if like you have some positive current weight left, you can take 0. But in general, you should try to keep things as generalized as possible. Like if it's not possible, then we don't return. Like what is our definition, that what is the number of ways, what is the maximum profit that you can create using I and W weight in current position. So if you if you design the states in that fashion, okay, you can write this 0, but like it won't matter in this problem. Just in some other problem it might. Okay, so let's keep it 0. It's fine. So if my current item's weight is less than equal to the current W, then we can take this particular item and we can go to I minus 1, right? Or we could just go to I minus 1 without taking anything, and that is going to be our answer. So we just return answer. Okay, so that's our DP. And now just to like make this DP complexity go from exponential to linear in like n into W, something like that, what we do is we create a memo table. Okay, and we initialize the memo table with something not possible. So I'm assuming that the profits can only be positive, because the profits can always be positive. So I'm just mem setting the memo table with -1, because -1 means that it's not yet visited, it's not yet calculated. Okay, so if dp of I comma current W is not equal to -1, that means it's already has been calculated and it's not going to be DP, it's going to be memo, right? So this, if it's calculated, then we return something called the value that is already stored. Line 18. So this is basically memoization, that what we are doing is we are just storing whatever we are storing. Okay, 22. So this is basically that if my weight is less than equal to my current weight, then then I might have reached this particular current weight by taking the ith item, right? So I might go to the previous, like from at the ith minus 1 step, I had this much weight, and then I had the profit of P of I. It should be I. Okay, so we are solving the 0 1 1. Like we can take one item only once. We are solving the first version first. Okay. So this should be the transition, and so we are basically writing this particular recurrence over here right now. This particular recurrence, this first recurrence, that we can go to I minus 1 and W minus WI plus PI, or this. That's what we have written in the code, right? And if it's not calculated, then if it's already calculated, then we are returning, or else we are calculating, and before returning, we are just storing that in the memo table. Okay. Makes sense? That's something we are storing in the memo table. So that next time whenever it returns, it can get that value from the memo table, right? So that we don't have to calculate. And that's all. I think that's all. Now, how do we get the answer? So the current weight can be anything between, like from 1. So after processing all n elements, what is the different, what is the max weight that you can create, that okay, what is the maximum value profit that you can create. So let's suppose that's 0 initially. Okay, so for integer I equal to, let's say 0, I is less than equal to the maximum weight w, I plus plus, right? Now the answer can be max of answer comma the maximum profit that you can create with all n element processed and their weights to be equal to I, right? Their sum of weights to be equal to I. Make sense? So anyways, once you make this memoization, using this dp function is okay, because this function will work like a constant array like access, right? Like it will, so that's the beauty of dp, because once you like write a function and you make it an array, it's just like accessing this array or else computing this function once. Okay, so now you can use this function as if you are accessing this array. So whenever you need, just call this dp and it will give you the, either it's from the array or it will compute it once. That's the whole idea of dp, right? So that is all. And then why we are keeping it I, because the sum can be any weight between 0 to weight, right? We can reach any weight 0 from 0 to w. Okay, so from that we can just get the answer. In fact, in this particular state, if we just called, because we made it 0, if we now just call dp of n comma w, it will just work. Like if we just call answer equal to dp of n comma w, this will work. But I'm not going into why this will work. You can think in this way because it's much more intuitive. Okay, make sense? So this is all in fact. Now you can print the answer. Okay, now changing it from like one supply for each item to infinite supply of each item, you can simply go from this to this, and that's it. That's, we are done. Right, now you will have infinite supply for each problem, each item in the problem. Okay, so the intuition for this would be, so the main intuition for this is what intuition we use for recursion is, leave it to the recursion to solve. Okay, that's the whole idea. That what we are doing is, we are having dp of I comma w minus wi. Okay, so like instead of going from I, so what we were doing is, we are at I comma w, right? Now we have to take, like at ith item we will decide on how many times we take the pair wi comma pi, right? So the ith item has wi comma pi, how many times we take this, and then we will go to dp of, let's say I minus 1 comma w minus x times wi plus p plus pi times x, right? This is what we will have if we take x number of times. Okay, so now what we are trying to do over here is, we are doing it smartly, and what we are writing is, okay, I don't want to go to I minus 1 immediately. What I can do is, I can go to dp of I to w minus I w1 wi once. Okay, I will take wi once and I get a profit of p of I, and from there it's, then again this particular function, this particular recursion has a choice that it can again take I, or it can now neglect I. Okay, so this can go to dp of I comma w, sorry, I minus 1 comma w minus wi. Okay, either it can go to this, or it can go to dp of I again to w minus, so if this was the value, then this would be w minus I comma into 2. Okay, plus p of I, so this will go to this value, and pi plus pi, when we will return, it will get 2 into pi. So again this can go to dp of I minus 1 comma w minus 2 times wi, or you can go to dp of I comma w minus 3 times wi. Okay, plus p of I. Okay, so now we will stop at this particular point, and now we will look at what we are doing over here. So either we are going to stop then and there. Okay, of course at this position we also had this particular transition, that we don't take any element of ith element. Okay, that's also a choice. But let's say we're trying to reduce this particular expression by taking any number of choices. Okay, so if we take once, we go to this particular, like taking once will leave us to this, taking twice will lead us to this, taking thrice will lead us to this particular state, and so on, right? So whichever is maximum, like out of this value, we will take maximum of these two paths, right? So if stopping at one is optimal, then you will stop at one, or else you will take twice and then stop, or else you will take thrice and then stop. So that's why this is building a max kind of recurrence between the states. And then that's why when we will call the max of this, it will automatically decide on whether to stop there or take more, okay? Because it's taking max from either stop here or take one more and then decide, okay? So that decision is already been done for this particular state, and from there you either stop and again take, or stop and again, so whichever is possible. That's how this particular state is working. Is it now clear that how this kind of infinite, like whenever you have this infinite supply kind of things, you just so keep this in mind, that you remain at the same object again. That's the main key of like state observation, and this is why this is working, okay? Because you leave the choice to the next state, and that will decide on how many times it will take it more, okay? Now think about this particular problem, that let's say if I give you that every item has some ki number of occurrences, okay? I have ki number of occurrences, okay? Every item can have some ki number of multiple number of ki number of times, okay? Ki number of occurrences of every item. Now in that case, we might have to loop ki number of times, right? In that case, we might have to loop from like either we take 0 times, 1 times, 2 times, and so on up to ki times. Okay, this is something if there is ki given to us, and in that case the like constraints might change a bit, but we can even optimize that particular problem. Think about this maybe if you get time after this, but we will take up this problem very late. Like this is a bit harder variation, but we will take up this later on, okay? That what if we have some ki number of times that an element can be taken, okay? This is one more version of knapsack, which is not very well known, but that comes up. In fact, in one of the contests that we set, like the last fortnight that happened, the seventh problem was on this exact logic, that how do we solve this knapsack elegantly? And in fact, there is a video tutorial for that. You can look at that. Okay? But anyways, moving ahead. That's a hard problem. Okay. But I hope these two states are now clear, right? How do we handle one element and infinite element? Okay. Now let's come at a next important problem, that is something called LIS. So I have one slide already prepared for LIS so that you don't have to explain everything. Is the knapsack one clear to everyone? So the two problems that we discussed, one is called 0-1 knapsack, that is every item can be taken either 0 or 1, or the other one is called like 0 infinity or unlimited supply knapsack or something like that. I don't know the name, but unlimited supply knapsack, right? What about the rest of the people? Are you understanding the recurrences, or is it all lost? It's understandable, right? Okay, fine. So then let's move to this next problem. I think this is one of an important problem, and you should definitely know this one. Okay. Now, given a array, you need to find the longest increasing subsequence. So from in DP, please note the definitions of subsequence and subarray. So subsequence is something which is like in same order like subsequences is a sequence which is like inside, which you can find by deleting any element from the sequence and merging the rest of them together. Okay. So it's like it can jump across the sequence. Subarray means like consecutive elements, right? Like continuous elements in the array. Okay. So finding longest increasing subsequence. So that is called LIS. So length in this particular so when we discuss, we will just consider the length that we want to find. Of course, the LIS is not just the length, but the subsequence itself. But let's say we want to find the length itself first. Okay, let's first try to calculate the length of this LIS, and that is something we want to find out. And then we will look at how do we calculate the answer. Okay, so let's say we want to find out the LIS for this. So that would be nothing but this 1, 2, 3, 4, because like these are increasing and it's a subsequence, right? And no other subsequence of larger size is possible in this array, right? Make sense? So this is the alias problem. Okay. Now we can solve the alias problem using a direct DP, which is very similar to the knapsack one. The idea that we use in that is DP of I is the largest alias that ends at index I. Okay. So this is a very common state that you will see in a lot of problems, that you have to find out the alias which ends at an index I. And this type of problems generally used in subsequences and subarrays. When you see that there is some subarray and subsequence in the problem, and it generally uses this idea of what we can extend from previous. Okay, so what is some solution that ends at some previous index, and can we extend it further or not? Okay, so let's try to calculate what we can do over here. So let's say, what is the longest alias that ends at index 2? Of course 1, right? Because there is no subarray more than of length 1 at ending at 2. That's quite obvious. Now, what is the longest subarray ending at 1? That is 1, because we cannot create this subsequence, right? We cannot take 2 and 1 together, because that is going to be like that is not increasing. Okay. Now let's talk about this 3. What is the longest increasing subarray, longest increasing subsequence ending at 3? That is nothing but this 1 and 3. Why? Because after 1 we can place 3, because 3 is more than 1. Of course, it's also possible you take 2 and 3. Okay, that's also possible. Okay. Now the way we got it, because the length for 1 was 1, and then after 1 we appended this 3, right? So we got this as 2. Okay. Now let's consider this 2. We can append 2 at the end of 1. Okay, whatever the length was 1. So it's like there is an optimal length of 1 ending at this index, that is of value 1, and then we can append 2 at the end of it, because 2 is more than 1. So this will be 1 plus the value at this. Okay, because it's less. Okay. Now for this 2 as well, it will be 2. For this 3, you can append 3 at the end of this 2. You can append, let's mark it with a different color. You can append 3 at this 2. You can append 3 at this 2. You can append 3 at this 1. You can append 3 at this 2. Okay, sorry, this 2. Okay. So now, which one should we extend at? Of course, all of the sequences that we are going to extend is going to end at 3, right? So it's better to extend the longest sequence, right? So here we have a number 2 which is of length 2, and there is a number 2 which is of length 1, or 1 which is length 1. So if we extend this particular sequence 1 3, that's going to be of length 2. But we can do better by extending this 2, because at 2 there was a length 2, that is this 1 then followed by 2, and we can append 3 at the end of it and create a length of 3. So the answer for this would be 3, right? For 4, we can append 4 at the end of any of the values, but we will append it to the one which is of the largest value possible. So over here, all of them are less than 4, so we can append it after any one of them, and the largest value we can see across those after which we can append is 3. So this value would be 4, right? In fact, from here we can see that, okay, the longest sequence will be this, because we took this 2 got its value from, let's say, this 1. So there is this sequence 1 to 2. Then this 3, let's say, got its value from this 2. So there was this 1 2 3, and then this 4 got its value from this 3 plus 1. So this is the sequence that we are forming, right? So the recurrence that we are following is dp of I is equal to, like, out of all different j's that lies between, like, before I. Okay, all different j's that lies before I from 1 to I, and the value at j should be less than value at I. Okay, if that is feasible, then only we can append a of I at the end of the sequence ending at j, right? So ending the longest sequence that ends at index j is dp of j, and we append 1 at the end of it. Okay, right? So this is like the idea of extending the answer. Okay, is this making sense, that what we are trying to do over here? Is this clear to everyone that what is this dp that we are writing? So basically for ith index, we are inside max dp 1. I did not get you. dp of I, no, this is dp of j. So we are looping over j from 1 to I. Okay, and for all possible indexes j, we are calculating which all indexes are valid, after which we can append a of I. So a of j is less than a of I, and for that index, whatever the optimal dp value was, we appended 1 at the end of it, and we got this value, right? And of course, by trivial value, yeah, max across all different values, like all different j which satisfies this condition, take the max. Okay, that's this notation, that max across all j's which satisfies this constraint. Okay, And of course, the trivial max value is 1 because at any index you can have one length sequence that is itself, right? Make sense? Now, time complexity for this would be, can anybody quickly tell me what is the time complexity for this? N square, right? Of course, because for every state we have order n number of transitions that can be there. Yeah, N square. Okay. Now our final answer for the whole array, like for the whole array, we need to find the longest increasing subsequence, right? So it will end at one of the indexes. So that is going to be this particular number, that max of dp of I, that is from I equal to 1 to n. And from out of these values, we will look at, okay, whichever is maximum, that is the longest sequence, right? Because the longest sequence will end at one of the indexes for sure, right? That's going to be our answer. Okay. So we solve this in order n square, but we will try to do it better than order n square. Okay. Let's look at that. So we created the solutions by extending some answer, right? Whatever the answer was dp of j, we extended it by putting a of I at the end of a of j, right? So basically we have a lot of like a length, and at the end there is an ending value, and we are appending the new value that we are getting to the end of that, right? Like we are trying to basically append 3 to the end of like whatever the sequence is at 3, at 2, at 1, right? These are the two values that are less than 3, and out of these we will try to append 3 to the ones that are possible, right? So basically, like when you are considering this particular element, when we are trying to solve the ith element, we basically have a lot of different sequences of all these indexes, right? From index 1 to, let's say, I minus 1. For all these indexes, we have for every position a length of sequence that ends at that value and that element's value, right? A of j. So A of j and the length, this is the only two things that it depends upon, right? Is this clear to everyone that for all these values, like when we are trying to calculate the LIS for this particular value, it is going to expand one of these values itself, right? It is going to expand one of these values, okay? And one of these values can only be extended if a of I is less than a of, sorry, a of j is less than a of I, and we take the length plus 1, okay? Take the maximum length, right? So this is what is happening, right? These are the two metrics that my extension is depending upon. Is this clear to everyone? Can I have a plus 1 if this is clear? Like these are the only two things, because any element after creating the sequence, any element over here does not matter, because the last thing is what after we will append it, right? Now we will try to, once we get this particular observation, we will try to optimize this further by looking at few possible cases, right? So let's say we have some element over here, we don't know what it is, but let's say these are some things which we have processed, okay? So we know that the answer, we quickly know the answers for these values. So for this, the length will be 1. For 6, the length will be 2. For 4, the length would be 2 because 1 and 4. Then for 5, the length will be 1, 4, 5. So 3 because it can expand at 4. For 6, we know the length would be 4 because for after 5, we can append 6, right? So these are the answers that we have already built. And after that, we will try to calculate the answer for this using these 5 values, right? So these are the 5 values that are outstanding, and out of which we will have to calculate the value, right? So like, can we prune these values? So these are the length and last values that are like possible. Can we prune these values out of like some of the values which are not going to be used for sure? Okay, that's what something we are going to use to improve on the time complexity. Okay. Now, how do we improve on this? Let's look at observations. Yeah, so that's not, so we cannot remove them permanently, right? Yeah, of course that is possible, that value less than ARR of I. So if this is AI, so only values that are less than equal to ARR of I will be valid. But after that, there might be some more index like I plus 1 where the value might increase and everything might become like feasible, right? So we want to prune this in such a way that it will never be optimal to take that particular element in future again for any element after that. Okay, any element after that. Make sense? But we just cannot do it based on ARR of I only. Okay, so we will just do some general observations that, like, with same last value, okay, with two elements ending at the same last value, we only keep the one which has the maximum length. Does this make sense? How many of you think that this should be this should be done? Because think about this particular case, that there is a one sequence which has of length 2 and ends at 6, and there is a sequence which ends at 6 and has length 4. Now any element that comes after this, if it is more than 6, then it will of course append at the end of this, right? Why is it going to append at the end of this? Because this is of course going to give us the same value, and of course is going to be better than that. So this is something that we can of course use to prune, right? Is this clear to everyone, that if the last value is same, we keep the larger length? Okay, this is observation 1. So out of these we can see that, okay, of course this 2,6 can be pruned. Like there is 4,6, there can be some subsequence with 3,6 as well. Like I have written this redundant, but like let's say 4, 5, 6, this is also subsequence, right? But we don't keep this because there is 1, 4, 5, 6, right? So all these things will get removed, right? These things can get removed. Okay, so these things will get removed. Let's say we appended one more element 3 and we got one more, like for 3 the answer would be 1, 3, right? Now next observation, with the same length, like after this, for any more element with the same length, we keep the pair with the smaller last value. Okay, like if there are two sequences which have the same length, okay, it's always optimal to keep just the smaller one, the smaller last value one. Is this making sense to everyone? Like will this be optimal every time? Because the smaller the last value is, the more freedom we have to append at the end, right? The more space we have for the next element. So anything that we can append at the end of 1, 4, we can of course append at the end of 1, 3, right? And the length will be same. So why to keep this one? Like we can remove this, right? So we can remove this length 2, 4, because 2, 3 is of course better than 2, 4 at all positions, right? Is this clear to everyone? Can I have a +1 if this is clear to everyone? Okay, now if this is clear, then with these two observations we removed a lot of things. Okay, I've removed all of the things, and now we will be left with things like there would be some lengths and there would be their like last value, right? What is the element at which it's ending? Okay, so there will be some elements which are like there will be left, these are the leftover elements like for every length. So now if you note that with same length we can have only one value, which is the smallest value. Okay, and with the same last value we can have only one value, which is the largest length. Okay, so now for one particular length there will be only one value left, okay, after pruning everything. And if you note this particular thing, that if you sort it by length, the last value will also remain sorted for sure. Okay, because think about this particular case, that why is, like if there is this property that will automatically hold. I'm going to explain why. Now this is the main crux that allows us to do the optimization by going from n squared to some smaller complexity. That if we sort, like after doing all this pruning, if we just keep things in the sorted order of length, our values are also sorted. Because let me think about this particular case, that I had 3 over here. Okay, if anytime I get any value which is more than 3, I will append it only after 3, right? It will only be appended after 3. So at all times this particular sorted value is always maintained. So if I again get some new value k, if it is more than k, it will always be of length greater than equal to 3 only, right? If I get a value 3 new, like there would be some length I will need to calculate, but the value would be k. This particular value, this length will always be more than 2 if k is greater than 3, because k can append at the end of 3, right? So if we keep doing this pruning at every step, this sorted value is maintained at all times. This is like an invariant that we call that. This is called invariant, that at all times this remains sorted, because every time we are appending a new element, we append at the end of the largest, like the largest length possible. Like after that we could not, like let's say the next element is 4. Okay, let's say the next element is 4. So that means we try to see which element we can append it after. Okay, so we can append it after 1, we can append it after 3, we cannot append it after 5 and 6, right? So we will append it after 3 for sure, and we will create a sequence 3, 4. The length is 3 and the ending value is 4. Okay, so now of course this will update something after this. Okay, and it will never change this particular sorted property for these elements. And what we will do is, instead of inserting this, since this length and this length become same, we will replace this index with whichever value is smaller. Okay, we will replace this index with whichever value is smaller. And at all possible cases, this will always be the smaller value. Because why will this always be the smaller value? The new element will always be the smaller value. If it is not the smaller one, if it is the larger one out of these two values, then we could have inserted it after this and we could have got a length more than that, right? If this 4 that we got would have been larger than 5, then we could have appended 4 at the end of 5 and we could have got 4,4 higher length, right? But we are getting this particular thing as 4. This is smaller than 5, so that's why it can always be like after 3 and less than 4. So it has length 3, so of similar length we can have only one sequence that is of length, like that is ending at 4, so we will only keep 4. Okay, so this particular property holds true at all positions. This is something that we will leverage. So look into the idea that, okay, at every position we will maintain. So this is the sequence that we had, right? Like after this particular sequence, like let's say 1 6 5 4 5 6. Okay, up till this point. Okay, so 1 will have length 1, 4 will have length 2, this will have 3, this will have 4. Okay, so anyways, this got pruned. Okay, so now next element came as 3. Okay, so find the length of best 6. Like what is the best sequence that we can end at 3? Like what is the length, longest increasing subsequence that can end at 3? That is going to be 1, right? Like that is by appending after 1, right? We can append 3 after 1. We cannot append it to anyone in this position, right? We are just changing this particular notation over here into an array format. Okay, we are just keeping the lengths over in this dimension and we are just keeping the values over here. Okay, anyways, we know that this and this both remain sorted at all times. That's what we proved over here. Okay, this is an invariant property. This is that is being maintained at all times. Okay, now when we have to place 3, we will find out, okay, after this 1 we can append 3. We cannot append it after 4 or anything after that because it is sorted. Okay, so this is the last element after which we can append. So 3 will have, what is the LIS value of 3? Like what would be the longest increasing subsequence ending at value 3? Any idea? 2, right? Yeah, this will be 2. So now we have a 2, 3 pair that exists in the set, if you remember, right? This kind of set. So now we'll have to do the pruning. So now once we have a 2 with the same length, we keep the pair with the smallest last value, right? So like length 2, 3 exists, but 2, 4 also exists. So which one do we keep? 2, 3, right? So we will update 3 at this position and we will get like this 3, right? And like since this is sorted, we just place it at length. Like we can find out which position we found out after which position from which we appended to like 3 at. After 1 we appended 3, right? So the next position is where we place it. Okay, anyways, because that's going to be the position where we have to place it, because that is something we could not take, right? We took this, but we could not take 4 because after 4 we could not place it. So this length plus 1 is the value for this, and this is more than this, but this is the initial value 4 would have been greater than equal to 3, then only we could not place it after 4, right? So that's why we could place this 3 over here, because we could update it, right? And if we just look at the implementation, if this all pruning and all things look difficult to you, this is a very simple code that you can use to find out the LIS for any array. That, okay, you have an vector of int ARR, so you just keep a vector. Okay, so whatever the array that we are talking about, this particular solves, this is the solves array that we will build. Okay, the solutions that we are building. Okay, so initially the solves array is empty. Okay, now we will keep on iterating on the elements of the array, and if solution is empty and or even the last, like v is more than the last element of solution, we will maintain the sorted property. So we will push it back, or else we will do a lower bound and put it there. Okay, so let's quickly run this on one sample example. Okay, so let's say we just take this particular example and we like first it's empty, so of course it directly gets appended to solves. Okay, then we come to this for 4, we know that 4 is more than 1, so we can append 4 at the end of this particular condition triggers, right? So we put 4 at over here, then 5 comes over here. So 5 is also more than 4, so we can put it over here. Okay, again this condition. Okay, next 2 comes up, so 2 is not more than this, or solution is not empty, so we come to this. Okay, so then we do lower bound. Okay, so we find out the first index, like iterated to the index which is which is greater than equal to 2. So the iterator to that will return this IT, okay? And we just update this particular position to 2, because this is from the logic that we discussed over here, that after, like, this is the first element which is greater than equal to 2, right? So the element before that was less than 2, and we could append 2 at the end of that, so the length will be at this position, and 2 is of course like less than equal to this element already present, so we just update it then and there, okay? Make sense? So we update the solves, so the solves array now becomes 1 2 5, okay? Make sense? Now we come to 4. So now 4 cannot be appended at the back, so we again go to this particular condition. So since it's all again sorted, we quickly do a lower bound, and that will trigger this iterator position, so this will become 4, okay? And then we will come to this 6, and 6 can be appended at the back, so this will be the final solves array. And if you see what is the like answer finally, the solutions dot size, that find out the solution size, okay? And that is going to be 4, okay? So the solves final size is 4, so the longest increasing subsequence of this particular array is 4, okay? Make sense? Is this logic clear to everyone, like what we all did, what we did just now? Can I have a +1 if this is clear? So this is just an implementation, like this is just like a standard implementation that you can follow to write the code neatly, okay? Coming to that, that's a good question. In fact, it's not always necessary, okay? So let's say first let's look at time complexity, and then we will look at no, solves will not be, so that's one caveat. Exactly. So let's first talk about this time complexity. What is the time complexity of this particular approach? Can someone quickly tell me that? Like if the size of the array is n log n, right? This is n log n in total, okay? And now so this particular alias approach works in n log n, okay? Now the thing is, this particular alias approach, the final solves array is not a subsequence of the that is alias, okay? Note this. Let's try to think about just this much chunk, that 1452, okay? This much chunk is there, okay? So we built it in this fashion, 145, and then we did a lower bound for 2, and we replaced this, okay? So this was it, okay? This was the final state. So the size was correct, but if you think about it, is this the correct alias that the array has up to this much? Is this the correct alias? No, right? So this does not find us the alias, but of course you can find, like, so if you have understood this particular logic, let's talk about 2 follow-up questions, okay? So how do we find the sequence and not just the length, okay? So how do we find out the sequence that we have to do, right? That we have to find out if we had to find out the longest increasing subsequence, how do we find that sequence and not just the length? Okay. The second question is, what if we had to find out longest non-decreasing subsequence? Like in this particular case, let's say we want to find out this sequence, that okay, it's okay to be elements to be equal, but it's not just decrease, okay? It's not decrease. It should be either equal or increase, okay? How do we find this type of sequence? Okay. So something similar. So think about this particular problem. I will not readily give you the solution for this particular problem. Think about this. This is a good exercise to think about how do you find the sequence, okay? How do you find the sequence which gives you the last? Okay? Make sense? And like, so if you understand this particular process, okay, the process that we did, you should be able to like write some extra code to print the sequence as well. Like a quick hint, like try to find out like which position were pushed at what place, like where it was kept, okay, and process from back to front, and that should help you to find out the sequence. I will not give you much of hint like how do you solve it actually, but I will just give you a quick idea that if you can track which position where was placed at which position, And then if you try to see the sequence in reverse order, you should be able to find out the longest increasing subsequence, at least once longest increasing subsequence. So is this n log n, like, is this approach of n log n is clear or not? Like what we were doing just now. Is this clear to everyone? This is a very important technique, and this you will see in a lot of problems. Okay. And this has even started appearing in coding tests and every place as well. So nowadays coding tests also ask n log n approaches. Now let's come back to the original sheet quickly. Okay, so I think we have already been taken up a lot of time. So if we quickly sum up things, I will maybe take up one extra session to cover up some more questions. But the idea is we talked about a lot of states today. One was like just I, comma, limit. So if we want to generate sequences in increasing order, right? So we use some sort of state which is I, comma, limit, which is like we have processed this much, and we need to generate things greater than equal to limit next, so that things don't get repeated, right? So note that whenever in a problem you need to remove permutations, always generate in sorted sequence. That's the most frequent idea that is asked in such problems. Okay. Then we talked about like knapsack DP and its two variation. First one is like 0 1, and then other one is 0 infinity, like it's just 0 infinity. Okay. So the idea for this is also important, that how do you optimize the transitions over in the infinite case, that instead of going to I minus 1, just go to I itself and keep the choice of repeating the element again. Okay. That's the main idea that you can use in this 0 comma infinity. Okay. Now next we talked about like the subarray sum, which is, and the LIS n square dp. These were both dp of I, which is the best subsequence or best subarray ending at index I, right? And which is also very common in a lot of questions. So this is something that you should keep in mind, that whenever you need to find, whenever you need to decompose subarrays or subsequences in DP, this might be a possible state, that what is the best dash ending at an index I, okay, ending at I, okay, this is one possible state. Okay. And then we looked at order n log n LIS, because that's quite like that's the most optimal way in which you can do the problem. Okay. Also, let me give you one particular problem that you can think about on your own. This is also coming up in a lot of places right now. So let's say you are given two sequences, okay? So there would be one question, something called LCS, okay? Longest common subsequences, okay? I'm not giving the name, like this will be there in the practice problems. You can look at the LCS, and this is just nothing but longest common subsequence, okay? Longest common subsequence, okay? So this is nothing but like find the subsequence which is common to two strings or two arrays or so on, right? So given two arrays A and B, which contains, let's say, numbers, okay, 1 3 5 7 9 4 3 2 9. Let's take this 4 3, okay, something like this. So let's say array A contains all distinct element, okay, contains all distinct element, okay. So find out the longest common subsequence of these two arrays, okay, and the sizes of array A is up to 10 to the power 5, and size of array B is up to 10 to the power 5. Okay, so like this is not a question of longest common subsequence, but still the question is, given two arrays A and B, A has all distinct subsequences, distinct elements, but elements can be up to 10 to the power 5, 10 to the power 9. Okay, elements are individually very large. Okay, and A and B are two arrays given to you. You need to find the longest common subsequence of the two arrays. Okay. Let's discuss this. This will hardly take maybe 1 or 2 minutes. Any ideas on how to solve this one? So of course, like I hope some of you might already know the n squared dp, like n into m kind of dp in longest common subsequence. For those who don't know, they will look up, like this is just some extra. But how do we solve this one? This does not, in fact, this problem does not need LCS states or dp or anything similar. It only needs things that we have already discussed today. So you have to find longest common subsequence. So one of the common subsequence would be something like 4 comma 4, 3 comma 3, 9 comma 9. Okay, this is two common subsequence. This is one common subsequence, and this is the longest possible, right? So find longest common subsequence of these two arrays. Any ideas? Okay, so let me quickly discuss this. If you have any idea, you can suggest. But I think this is a bit non-trivial, but still, this is a very nice idea that you can use, in which you can use the things that we have already discussed today. So since A is all distinct, let's rename A to the array 1, 2, 3, 4, 5, 6. Okay, let's rename this to 1, 2, 3, 4, 5, 6, 10. Okay, whatever is n. Okay, we will rename these. Since it's all distinct, we can rename, right? We can just, like, since it's a subsequence, we can rename it to, like, we can say, okay, 4 is 1, 3 is 2, 5 is 3, so on, right? So if we use this renaming and then like use the same mapping that we create on array B, we will get something like 1, 2, something x, which does not exist. Okay, then 5, then something does not exist. Okay, and then it turns out that if you want to find the longest common subsequence, how do we find it now? Like out of these two sequences, what is the longest common subsequence of this and this? Like any subsequence over here, like let's say there is 4. Yeah, it's alias of B. Okay, so you just need to identify that this particular problem can be solved with alias. Just transform the distinct one to unique ones, like 1, 2, 3, 4, n. So 1 is sorted. So if it's common between these two elements now, that means the top sequence will be sorted, right? For sure. So the other one should be sorted as well. So we need to find the longest increasing subsequence in this, and that you can solve in n log n using the technique that we discussed just now, right? Okay. So this is one more problem. So I think let's keep it up to this particular point. I hope the things that we discussed were clear. I hope could make some sense. Okay. So we discussed a lot of things on DP today, uh, like some of the basic states. We will also take up more states on the next sessions. Okay. Any doubts on any of the problems that we have today?